Can you hear my voice?
Yes, sir.
Yeah. Okay. So, welcome to this week 6 live session. Okay. So, what we do is in week 6, we have two topics. Okay. So, one is RH criteria. So, second is root locus. Okay, RH criterion and root locus. So what we will do is today we will cover these RH criteria and problems on RH criteria. Then Wednesday we'll see the content revisiting of root locus, and Friday session we will concentrate on the problems on the root locus. Okay, so we'll start with this RH criterion. So basically, you all know the characteristic equation. So basically, characteristic equation means, suppose if you have a closed loop system where you have k of s, and let's say you have g of s, okay, and you have feedback of h of s. Okay, so we have a summing point here. Let's say the input is r of s, output is y of s. So if you have this feedback control system or closed loop control system, so basically the expression for transfer function, closed loop transfer function, that is y of s by r of s, how could we write? So g of s k of s divided by 1 plus g of s k of s and h of s, correct? So here the this is the general form of the characteristic equation for the closed loop transfer function. Okay, so uh, if we are having these numerator and the denominator, okay, so this particular denominator, okay, so 1 plus g k h of s equal to 0, so that is called as the characteristic equation of the closed loop system. It means, so 1 plus gkh equal to 0. So this is the characteristic equation of this closed loop system. Okay. In general, the transfer function might looks like this, where we have numerator as well as the denominator. So characteristic equation means taking the denominator equal to 0. Okay. So the expression is in terms of powers of s. Okay. That is first part, characteristic equation. Hope uh, uh, you have any doubts in calculating this characteristic equation of closed loop systems. Okay, so once you have this polynomial equation, so you can write the polynomial by finding its roots, where the roots are p1, p2, p3. So you can write them as s minus p1, s minus p2, etc. equal to 0. So you can write this one in the factored form as this. So once you expand this expression, okay, you'll be getting something like this. So where this equation says that, okay, this equation says that uh, to make all the roots, okay, so to get all the roots negative values, okay, all these coefficients must be non-negative to get all the roots in the LHS side of the S plane, LHP side of the S plane, all the coefficients must be non-negative. Okay, or and all coefficients should have the same sign. All coefficients should have the same sign. That is the first condition. Okay, so to get all these roots p1, p2, etc., pn, to get all those negative values, that means to make the system stable. So what is the meaning of stability? All poles should be on the left hand side of the z omega axis. Okay, so to get all those poles negative values, all these coefficients, okay, so they must satisfy non-negative and same sign. Okay, that is first condition. Here, that is only the necessary condition. Why? Because suppose if you see this expression, if you see this expression, here we have, you see all these coefficients. What are the coefficients we have? 1, 1, 2, and 8. All those coefficients are non-negative. But if you see these roots, okay, so if you look at these roots on the j omega axis, so we have -2 here. So the another root is 0.5 plus plus or minus j 1.9. So one root is here, another root is here. I'm sorry, that is plus 0.5. So that means this one, this is minus, this is plus 0.5. So and one root will be here and the root is here. So that means this one is plus j 1.9, this one is minus j 1.9. So it means that, so whatever we have discussed, all these coefficients positive values, okay, so all these coefficients are non-negative to make the these roots positive. That is only the sufficient necessary condition. So even though here roots are, even though the coefficients are positive, roots are sometimes negative also, sometimes positive also. You can see here. So the -2 is on left side, whereas the other root is on the right side. So hence the system is unstable. Okay, I think this point is clear. So it means that, so having all the coefficients non-negative or same sign, it is only necessary condition, not sufficient. Okay, so basically this RH criteria, so will give us this, will find this sufficient condition. Okay, so where this sufficient condition, this RH criteria will have these two steps. One is, first we need to generate this RH array. Then based upon that array, we will decide the how many poles are on the left side of the j omega axis and how many poles are on the right side of the j omega axis, whether the system is stable or not. Okay, so let's see the RH criteria finding the RH array. Suppose you have this polynomial, characteristic polynomial. First what we do is we put that polynomial into this form. Okay, so you can see here, first we will place here, so we will write this polynomial as like this. So s power n, s power n minus 1, s power n minus 2, etc. Last one is s power 0. Okay, so we will write the terms in this way. An we will write here, an minus 1. Next we will write an minus 2 here, an minus 3 here, etc. we will write. So that is what this expression says. So after finding this first two lines, it means that all the coefficients will put in these two rows alternatively, an minus 1, an minus 2, an minus 3, an minus 4, an minus 5, etc. Then using this all these coefficients, we are going to find these bn minus 1, bn minus 2, bn minus 3, cn minus 1, cn minus 2, cn minus 3. So in that way we will fill this entire table. Okay, so this is called as the RH array. RH array. So we'll see that example, you will understand easily. So now, as I said, first coefficients we are putting into these two lines. Then we are going to find these B row and C row. So you can see this first one, Bn minus 1. How do we find Bn minus 1? So we multiply An minus 1 and An minus 2. You can see here. Then An and An minus 3. You can see here minus. So divide by this expression an minus 1. Okay, then bn minus 2, how do we calculate? So again starting from here, an minus 1, an minus 2, an minus 5, divide by again this an minus 1. You can see here. Okay, so that is how we will calculate bn minus 3, 2. Similarly, we can also do the calculation for bn minus 3. So that is how we will calculate for b row. After that, once we have this b row, now we calculate the cn minus 1. So using this row and this row. You can see Cn minus 1. So Bn minus 1, An minus 3 multiplication. Then An minus 1, Bn minus 2 multiplication divided by this Bn minus 1. That is Cn minus 1. Cn minus 2 is similar way. These two terms multiplication, these two terms multiplication and subtract them, you'll get Bn plus 1. So that is how we will fill this entire table. So then after having this RH array, so we are going to decide. Okay, so we will check the sign changes from between each rows. So from this row to this row, is there any sign change in the uh, first column? Is there any change in the first column? It means between this element to this element, is there any sign change? So no sign change. Let's say, for example, here also no sign change, here also no sign change. Okay, let's say here we have some sign change, here we have some sign change. Okay, so if there are no sign changes at all, we say system is stable. If there are sign changes, we say system unstable. So number of sign changes equal to the number of roots on the RHP. Okay, we'll see the examples so you'll understand it in a better way. So this is clear. What we do is, first we will prepare this route array. After having this route array, so we will only concentrate on the first column. So we will check for the sign changes. If no sign changes, stable. If there are any changes, unstable. Okay. So uh, you can see this example. So first, let's say we have this equation. We'll be writing the terms like this. Let me write it again here. You'll understand. S square, S power 1, S power 0. So the terms are, first one is coefficient 1, second one 4, then 9, 10. You can see that. Now this term, what we do? So 4 multiplied by 9 minus 1 multiplied by 10 minus 1 multiplied by 10 by 4. So that will be 26 by 4. Okay. Similarly, this term is nothing but, so uh, this multiplied by 10, and you can put 0 here. 4 minus 0 divided by this term. So that will be 4 by 10. Okay. So 26 by 4 and 4 by 10. Now you check the sign changes in this column. Okay. You can see here 1 to 4. Sorry. So you can see here 1 to 4, no sign change. Then 4 to 26 by 4, no sign change. Then 26 by 4 to 4 by 10, no sign change. Hence the system is stable. Okay. So this is the basic example. So then we'll have two special cases. So first case is what you are doing every time. So you are taking multiplication 1 multiplied by 2. Then you are taking multiplication 1 multiplied minus 1 multiplied by 2. Then you are taking divide by 1. So if you do in this case, what happened? 1 multiplied by 2 minus 1 multiplied by 2 divided by 1. So what you are getting 0. That means this term is 0. So while calculating this term, usually what we do, so you calculate this and you calculate this, divide by 0. Okay. So what you get here, so you are about to get infinity. Okay. That is all because you have 0 here. That is one special case. So what we do in this case is, simply wherever we are getting 0, this happens only when if you get 0 in the first column. Okay. So what we do is, we will replace the 0 with a small number epsilon. Okay. Then carry out the calculations. At the end, what we do is, we will make that epsilon goes to 0 and see those terms and check for the sign change that we will see in the example. Is this clear? Any questions? Any doubt here? So any doubt here?
Sir, how are you taking the numbers like 1, 2, 3, 1 to 15? in the table.
Let me show you again. Yeah, yeah, let me show you again.
That's actually unclear. Means,
Yeah, yeah, yeah. Let me tell. So now you have this polynomial. Yes.
yes,
So first what we do is we start with the upper highest polynomial. We write the polynomial
yes,
in this way.
yeah.
Okay.
That's also
So
understood.
clear. Now we'll consider only first two rows and fill these coefficients. What is the coefficient here? 1. Here 1. Correct. So we fill them like this. 1, 1. Clear.
Okay,
Then 2 will goes to here alternatively. This 2.
okay,
Then this 2 here. Then this 3 here. Then 15 here. Is this clear now?
yeah, fine. Then
So
about
we'll
0 and
fill the
minus
first
12.
two rows. Which one?
0 and minus 12 is like we will do cross
No, no.
multiplication with.
Yes, yes, exactly. So this we are
Okay,
getting after doing the next step. So now what happened is here. So we are getting 0 here. We are
that's
getting
fine.
minus 12
Minus
here.
12.
Okay.
How we
Okay.
got minus 12?
Minus 12 is uh, this multiplied by this minus this multiplied by this divided by
Okay,
this. So
means
1
every
multiplied
multiplication is
3
with first
minus
row
1
only.
multiplied 15 by 1. Yes. Okay. That is minus 12. Clear?
So every time we divide, the division would
Yeah.
be from
First
the
element.
first row only. First
First row
row,
only.
the second one.
Yes. Yes.
Therefore, when it came zero, we are telling that divided by zero is your.
Yeah. No,
It
no.
comes
Next.
to
Next. When you are
1.
finding this, when you are finding, trying to finding this, okay, you have to divide by
Okay.
0. Yes or no?
Hmm.
So
Then,
that will goes to infinity.
yeah.
So you
Then what
cannot.
would be the then what would be the value after minus 12? Means the
That's
downward of
what.
50.
That's why this is special case. Okay.
Okay.
If we don't
Got it.
get 0 here, if we don't get 0
Hmm.
here, so we can
Okay.
we can continue our calculations.
Okay.
Like we have here, we did not get anywhere 0. Correct in this.
Huh. Yeah.
So we are calculating the calculation, continuing the calculations and checking the column for the sign changes. Okay, if we get 0
Yes.
only,
Yes.
this is special case. Okay, if we get
Okay.
0, what happened? This term, okay,
Will
it will
comes
become
infinity.
negative infinity.
So we will take
Okay,
epsilon in the part of
yeah. So
0.
yeah, here we take epsilon and continue the calculations with epsilon. Later, what
Okay.
we do is we take the limit. Let's say we are getting some term here in the function of epsilon, correct? So
Hmm.
then we take the limit epsilon tending to 0 of that term. Okay.
Okay.
Then check whether it is positive or negative.
Okay.
Okay. So because to decide the stability, what we need, we just need to check whether there is a change in this sign or not. Yes or no? So that's why we will check this limiting term, whether it is positive or negative. Once we get to know positive or negative, we can decide how many uh,
So
changes are there.
in this example,
Yeah.
what kind of function we are supposed to get? Should we calculate now or
Yeah, let's do the calculation. You'll understand.
yeah?
Okay,
It would be
so
better
now,
means to
yeah, yeah. Now you see we got epsilon. So what is
yeah.
the calculation? Can you tell me? Let me write this one as A. Okay,
Okay.
this term. So what is the A? Tell me. So
So
2
what should be
epsilon,
A? So it would
2
be minus
epsilon.
12. Acha,
No,
yeah.
this way first.
2
This is
epsilon.
the element
Ah,
plus
okay.
12 divided by epsilon.
Yeah, plus 12 upon epsilon. Okay. So
Yes.
it will
So
come
let's say
2
this is B.
plus 12
What
upon
is B?
epsilon.
Tell me.
Our B would be
Yes.
your
Hmm.
then we have to find one more element there, the
Yes, yes,
beside of
yes,
minus
yes.
12. Uh,
Yeah. So this will be 0. So that will be 15 epsilon.
Acha, yeah, fine. It would
Okay.
again come
Divided
0.
by epsilon. Correct?
This would be 0 into 15 minus, okay, it will come 0 upon 0.
No.
Wait. So, oh
Epsilon,
yeah,
no.
few
It will be
epsilon we are
15.
taking. So 15 epsilon upon epsilon. Yeah. Hmm.
Yeah, so is that clear?
So 15. Fine.
Now, let's say this is C, this is D.
B equals to 15.
Okay, yeah.
Okay.
So B will be 15. What is C? Can you tell me?
What is our C? So C would be
Yes,
our minus 12a upon a.
minus 12A B epsilon divided by A.
Oh yeah, sorry. B epsilon. Actually, I am eliminating it again and again
Okay,
because it's zero.
that is C.
Okay,
Yeah.
epsilon. Yeah.
Then D is 0 already because
Then
it has
D.
to calculate this one. No, I'm sorry.
So C is zero.
It has to calculate this. It has to calculate this.
Okay, so we will take this
Yeah,
all. Acha,
yeah,
all the way it comes zero only.
yes, yes. Now,
Fine.
let us say this is E. This is F. What is E?
So E is our CB minus AD upon C.
Clear?
Hmm. Okay,
So
then
now
we have to
substitute
calculate.
everything. Substitute everything. So
Okay, after
what
that,
do we have in the first column? There is no problem with this. There is no problem with this. Okay. So we have to check here epsilon tending to 0. Yes or no?
okay. Hmm.
First here epsilon tending to 0. That is positive only we
Yeah.
can take. Positive or negative. So let's say positive. Okay. Because that is 0.
Yes.
Now
Yeah.
this term, A term. What
Hmm.
is A term? Let
A
me
term
add
is our
this. Just a
2
minute.
epsilon plus 12 upon epsilon.
Yes.
We can take a new page, I guess. Means it would be good.
Yes. Yeah, I can directly go from here. It will continue. Okay. Sorry for the trouble. So now this term, A term. Okay. So what we do, we take limit epsilon tending to 0, A. Can you hear me? Hello. Can you hear me?
Yeah, yes, sir. Yeah.
Yeah, yeah. So limit epsilon tending to 0. What is the A expression? 2 epsilon plus 12 by epsilon. Am I correct?
Yes.
So what is this limiting is going to be positive or negative? It will be positive value. Yes or no?
It's 2 plus positive.
Yeah. So we will just check only whether that limiting is positive or negative only. We don't require value.
Means
Okay.
how we are deciding, like if I take
Yeah.
divided by
For
epsilon,
example,
it will come 2 plus 12 upon epsilon,
yeah,
so that will
limit.
come 2 plus infinite. Yeah.
No, limit. So you take epsilon out. That will be like 2 plus 12 by epsilon, correct? By epsilon.
Yes, that's only I'm saying. Yeah.
So that will be like 2 plus 0, no? So sorry, a positive value total.
Yeah. Okay, means it will tending to positive infinite.
That's it. That's it. So we look for only positive or negative. That's all. We don't check the value.
Okay,
Okay.
we
So
are
that
not
is A. Next, yeah, yeah. Next we will check for C also. We'll check
for
for E
C.
also. Yeah.
Okay. Yeah, fine.
Okay. So then we will see. Uh, is there any sign change here?
Sign.
There is no
So
sign change. Correct.
how would we decide that there would be sign change? Means like
This is
A
plus
is
one.
coming
This is
positive.
plus one. This is plus one.
Yes. Hmm.
Okay. Next to 1 to 0. No sign change. Correct.
Yeah. Acha. Okay. Now 0 to A is also no sign change.
Yes. In that way we will check. Okay. If there is no sign changes at all, Okay, we'll say
Okay,
system is
then the
positive.
system is stable.
Yeah, system is stable.
And if there is any
Okay.
sign change in between or at
Yes.
last, I can say
Yes.
that the system
So
becomes unstable.
system unstable, also number of sign changes.
Okay.
Okay, we will look for how many
Number
sign
of sign
changes are
changes.
there.
Okay.
That many
How
poles
many
are in the
change
right
into
hand side.
negative, positive?
No, no, that
Hmm.
many poles are on the right hand side.
Hmm.
Okay, now suppose if there are two sign changes, let's say. Okay,
Hmm.
so
Yes.
right side, how many poles will be there? Two.
Two. Okay.
Yeah,
The number of sign change will decide that
mm,
how many poles are on the
right hand
right
side.
side, right side
Yes,
of the y-axis,
right
or the
side of the z omega
well,
axis.
yeah, right side of our this
Z omega axis. Clear?
z omega, j omega axis. Yeah.
Yes. So we have real axis, this one, and Z omega axis. Okay.
Yes.
This is LHP. This is RHP. For systems to be
Yes.
stable, we want all poles to be on the LHP only.
Fine.
Is this clear?
Yes. Yes. Yes.
Yeah. Any queries?
No, I guess we can
Yeah.
continue.
So if you solve one example, you will understand it clearly. Okay. So
Yeah,
this is
it's better
special
to take
case one.
examples.
This is special case one. Okay. Next.
Okay.
Yeah, you can see this same example. Okay. Here this is positive. Okay. This is negative. This is positive. Okay. How many sign changes are there? How many sign changes are there here?
Here we have only two times sign change happened.
Yeah. So from here to here, one sign change. Then from here to here, another sign change. So number of sign changes are two.
Yes, number of sign changes are two.
So
That
it
means two
means
poles are
that,
on the right side.
yeah, so total number of poles are five. Okay. So two are on the
Okay.
this side and remaining three will be on the this side. Clear? So system is unstable. Okay.
Yes, now I able to understand. Yeah.
Yeah. So only thing is that what you need to do is here the catch is, so for these terms, so you have to take limit epsilon is tending to zero. Those terms you have to check. Okay.
Okay.
So whether that is positive or negative, that you need to check.
Okay. Fine.
Okay. So here this is positive, this is negative. Is this clear?
Yes.
Okay. So this is true when we have a zero here. Okay. So that is special case one. Next, special case two. Now you see this example. So we have, you can write it here. So s cube s square s power 1 s power 0. Okay. So now what is the first two rows? 1, 5, 6, 30. Is this clear? So now what is this value is going
Yes.
to
Yes.
be 0, correct? Then this is already a 0. Okay. So now you are getting a situation that the entire row is 0, correct? The entire row
Yes, sir.
is 0. So in this case, what we do is, this is called as the special case. You get all the elements in a row are 0. Okay. In this case, what we do is, we'll form something called as the auxiliary polynomial. Auxiliary polynomial, what we do is, this is the row we are getting zeros. Okay. We will check this row elements, the row just above the zeros. Okay. So what do we have there? 5 and 30. Okay. What is the polynomial if I write? auxiliary polynomial a of s, that will be 5s square plus 30. We don't take 30s, we'll take 30. That means s power 0 coefficient. Is this clear?
Okay.
Okay, so
So
5s
how we
square plus
eliminate
30.
this SQ?
Sorry, no. If we get this row, we'll take s cube plus 6s. Got it? Because usually this row is odd number, this row is even powers. Clear?
Yes, that's already clear. Okay.
Yeah. So now this is called as the auxiliary polynomial. So now what we
Okay.
do is we take the derivative with respect to s. So that is 10s plus 0. Correct?
Okay.
10s plus 0. So now we will replace these with 10 and this with 0.
Okay.
This with 0. Is this clear? Now we'll continue the calculations. Okay. So you can see here we have replaced 10 and 0. Okay. So we continued the calculations with this 10. So we got 30. Is this clear?
Yes. Clear.
Yeah. So again we check the sign changes. No sign change, no sign change, no sign change. System is stable. Okay. But here you could see we cannot say directly system is stable. Instead it is marginally stable. Why? Because the roots of the auxiliary equation, they lie on the imaginary axis. What is our auxiliary equation? As
5
equal
square
to
plus 30
5s square plus 30. So what are the s here? S square equal to
minus 6 I
minus
have done.
6. S is what? Plus or minus j6. Okay, it means you have
Oh, yeah.
plus j6 minus j6. Okay,
Margin list.
so marginally stable. Is this clear? That is special case 2.
Okay.
Okay. So generally, when we have marginally stable, we'll get these three cases. Either maybe roots on this kind. Okay, so they are symmetrical to the real axis or symmetrical to the imaginary, or they are like quadrantal about the two axes. We may get the roots like this if you take the if you find the roots of this auxiliary polynomial a of s. Here, in this way, we will get the roots. Okay, so you can see this example also. So
The
first
last
two roots.
I want to ask how we decide this auxiliary polynomial means
Yeah,
in the
that's
last
what.
one.
Yeah. So here we'll get zeros. When we do the calculations for this row, we will get the zeros. Okay, once if we get all zeros in a row, then we'll
Okay.
go for the auxiliary equation. The auxiliary equation is nothing but the polynomial
The
of
above one.
this row.
Okay.
Okay, so that means
The
here 2s,
so
sorry,
always we are taking the second row or the row above the all zeros.
no, row above the all zeros. So
Okay.
it may come here.
Like just
No,
take an
no,
example. If I getting all zeros in the fourth row, then I will take
yeah,
auxiliary
you'll
equation
be taking third row.
third row. Okay.
Yes.
That
So
I
just
understand.
above the zeros row. Okay, here this is your auxiliary equation.
Yeah.
So you could do take that multiplication factor 2 out. You can write the same thing. So now you got what? 4s cube, 4s plus 0. So what you do? You replace this 0 with 4, this one with 4, this one with 0. Okay. Then continue the calculations.
Yes.
Continue the calculations. Okay. So now no sign change, no sign change, no sign change, no sign change. Okay. But here we have these auxiliary equation is giving repeated roots. Okay, so they are plus j minus j plus j minus j. Okay, so system can be marginally stable, and so we can also call it is as unstable. Okay, if you don't want to specifically mention, it is marginally stable. Generally, when we get this auxiliary polynomial, we say that is marginally stable. Okay, yeah. So this is about RH criteria and its method. Okay, so first what we do, we form RH array. Okay, so then we will check the first column. Okay, so and look for the sign changes. So if there are no
Yes.
sign changes, we say system is stable. If there are sign changes, we'll say that that many number of poles on the RHP side. Okay, then we saw the special case one, where if zero is existed in the first column, we will replace that zero with epsilon and take the limiting to the epsilon. Then special case two, when you have a row of all zeros. Okay, then we take something called as the auxiliary polynomial, then take the derivative and calculate the coefficients and continue the calculations. Is this clear? Any queries in the method?
Just wait.
Yeah. Okay, now we will solve some of the problems. You will understand it in a better way.
Can it be
Okay.
happen like in a
Uh,
row there are I should get three values, two are zeros and one is non-zero. Like here we discussed, either we are getting 1 0 and the second one we are getting
1 0 in the first column.
yes 1 0 in the first column, or
Other
either we are
when
getting zeros in all the columns.
yes,
So can it be happen like I am getting two zeros and one is non-zero, or like some of the columns are getting
two
zero?
zeros. Two zeros means first column is zero or not in first column element. That is important because you are going to take every division with that.
Sign.
No.
Okay, and the sign change also we are going to take from the first column only.
Yes. Yes. Only for first column.
Okay, that means first column is the main thing I have to
Yes.
see.
Exactly.
Okay.
Okay. Yeah. So let's see some examples. You will understand. Okay. So I come up with the solutions also. Later I'll give you this file also so that it is easy for you to check the solutions. Instead of that, if we start solving the problems, we cannot solve because the calculations are more. Okay.
Sir,
So
better
I'll
to
go
share
very
this thing
slow.
in our G space.
Yeah. I'll share this one also right after
Ah,
this
okay.
live session. Okay. So
Hmm.
here, so a system of spark ignition of automotive engine is given to you. Okay. So we have input as R of S, output is Y of S. Okay. So these gains represent different components in the system. Okay. Where K is the controller. Okay. K is the controller. Now our job is to find the overall transfer function first. Overall transfer function means y of s by r of s. Okay. Then once you have this overall transfer function, then you have controller gain k. Okay. Controller gain k. Okay. You have to give the range for k. So what kind of range we have so that system becomes stable. It means that if you take some k is equal to 2, if all the poles are existing on the left hand side or not. Okay, you have to give some values for k, right? So k from this value to this value, so the system becomes stable. So your answer should be like this. Okay, so we'll try to answer this using this RH criteria. So first part is to calculate the overall transfer function. Now you could see I have taken the same image. Okay. So what we do is we try to reduce this block diagram first. So first we are considering this part. Okay. So how that part looks like. So it simply looks like G. You have a feedback H. Okay, we have summing point here. This is input, this is output. Okay, plus minus. So this inside part, the circle inside part. Okay, so what is the transfer function? Y by r is g by 1 plus gh, correct? So that's what we have taken, g by 1 plus gh. What is g here? K by s plus 1. What is h? 1 by 5. So once you substitute this g and h into this expression, okay, this expression, so you're getting z1 as its transfer function as 5k by 5s plus 25 plus k. Is this clear? Any doubt in this g1 calculation?
No,
No
only
doubt.
this k upon s plus 5 and 1 by 5 we are taking.
Yeah, yeah. So yeah, k by, yes, yes, this part only, the circle part.
Okay.
Okay. So once we have that, g1 will become one simple box of value, this one, 5k by 5s plus 2s 25 plus k. Then after that, so g1 of s and 1 by s plus p, how they do, how they looks like? They looks like this: g1 of s plus 1 by s plus p, correct?
Okay.
Yeah, so now we are calculating this g2 of s, which is nothing but the uh, total transfer function by these two. We'll be multiplying g1 with 1 by s plus p. This combination is called as the cascade combination. When you have something like this, we'll multiply both g1 of s multiplied 1 by s plus p. Clear?
Yes, clear.
Yeah, so that will give us g2 of s. Okay,
Hmm.
so this is the expression. Okay, so now you see this inside everything we have replaced with the g2 of s. Is this clear? You can see
Yeah.
inside we
So
have
the
replaced
bigger
with,
function is like g2 of s, and 1
yes,
by 5 over it and 1 upon s.
yes, yes, yes.
First, we also take g3 of s of this both. Okay.
Yeah, now g3 of s also similar way. So how we are calculating z3 of s? We have z2 here, we have summing point here, we have output. So this is the feedback now. This 1 by 5 is the feedback. Okay, so this is y, this is r now. Okay, z3 how we are calculating? This way. So z2 by 1 plus z2 multiplied 1 by 5. Okay, that is z3. Clear? Okay, so now we are getting an expression. After that, how z3 and 1 by s are connected? In the same way previously, in this way only. Correct?
So,
Yeah,
okay. Yeah.
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 Ask me the doubt. No problem.
No, no, means clear.
Yeah.
Actually, I was
So
taking gh upon 1 plus gh. It's g upon 1 plus gh.
yeah. So now z3 and 1 by s, they are also connected in this way. Okay. Hence,
Yes.
the total
That's
z4 becomes
g4.
what? Z3 multiplied 1 by s.
G3 multiplied with 1 upon s.
Okay.
Okay.
Yeah, you can see.
And
Yeah, this
uh,
is
and we
G4
also
is,
take
yeah, yeah,
nothing, nothing, nothing. We can.
yeah. So this is the G3 expression, this one, okay, and Z4 is this, okay. So finally G5, okay. So G4 by 1 plus G4. So final expression is this, okay. So that is nothing but Y of S by R of S for the whole system, okay. So now this looks like what? This has what? Numerator by denominator, okay. So now we take the characteristic polynomial. I told you starting of this class, this is the closed loop transfer function. Okay, closed loop transfer function. For a closed loop transfer function, what is the characteristic polynomial? So taking its denominator equal to 0. It means that this term equal to 0. Is this clear? Any queries? If you're having any
No
queries,
queries,
ask
but the
me.
expression is
Yeah,
very big.
yeah. You just need to check this. Okay.
Yeah.
So then we will expand this expression
It's
and
just like we have to do by ourselves, then we will check
yeah, we'll get to
with
know.
this.
Okay. So now this is the characteristic polynomial. Okay. In this characteristic
Okay.
polynomial, we need to check for that p that is system constant for p is equal to 2 and p is equal to 0. That is given in the question. Okay. For p is equal to 2, this is the expression. Okay. So after simplification, we got this. Okay. Now we are going to apply the RH criteria.
Okay.
Okay, so what we do, RH criteria. So we write s cube, s square, s power 1, s power 0 because the highest power is s cube, s square, s and s power 0. Okay, clear? Okay,
Wait. So we are getting our equation from s cube. So
yes, yes,
there would be s cube s square s to the power one and s to the power zero.
yeah. So the s cube coefficient is 25.
Yeah,
Okay,
and that is 250 plus 15k. Okay,
now
and
s square coefficient is here in the down.
that is
Then s
175 plus
coefficient,
7k. Okay, and the
yeah,
25k. Okay,
yes,
noted.
s coefficient
Here,
is here. Then s power 0 coefficient here. It
yes,
means that
yeah,
all the coefficients we will put it in the first two rows. Okay.
yeah.
Then, so this term, so this multiplied this, that is 175 plus 7k multiplied 250 plus 15k minus
Okay,
25 multiplied 25k. Clear? Divide by this term.
divided by 175 plus 7k.
Yes. Okay.
Okay,
That is this
yeah.
term. This term is 0 because there are no other terms here. Okay. Clear? Now we
Acha,
need to
yeah.
find,
We have no other
yeah,
terms. Okay, fine.
yeah. Now we need to find this term. Okay, what is this term is going to be?
This term
This
going to
term
be
multiplied
this
this
term
one. This term multiplied this. What do we get?
zero only. So one.
We'll
We
get to
will get
25k.
25k. Yeah, we will get 25k.
Yeah, this one multiplied this and this one multiplied this. Divide by this term only. So 25k.
Multiply by 25k. Yeah, we will get 25k.
Okay, so now what is we got our first column elements. Okay, so first column elements,
We
what
have
we are
to
going
put
to
it
do
in with
is,
the first column only.
yeah, so first column elements either what is the condition for stability? All has to
So we
be
will check
same sign.
the sign change. Yeah,
Okay, no,
they
if
have to
there
be
are no
same.
sign changes, only system is stable.
Hmm.
Okay, so either all
Yeah.
has to be negative or all has to be positive.
Okay. In
Okay,
the case of it should all be negative or it should all be positive. Okay.
yeah,
The
so
number
now
of sign
25
changes
is
should be
already
negative.
positive. Okay, so I'm
Hmm.
taking all these elements are also positive. Okay, so like this. So first this element
Hmm.
for
K
system to
should
be
be greater
stable,
than zero.
for system to be stable,
Okay.
25k greater than 0.
Now we have
So
to
k is
find
greater
what
than
should be
0.
the value of k.
Yeah, we wanted to make the system stable. So what is the k
Stable.
range that we need to find?
What would be the range of k? Got it.
Yes. So then second expression 175 plus 7k is greater than 0. So I got k is greater than minus 25. Then from the third expression, okay, So what do I get? K is greater than or equal to minus 17 plus or minus a 9.88. Okay. So for these three, what is the common range? This is the common range. Is this clear? Any
Okay,
queries?
so from all the what should I say? From all the ranges, we will take
From
union or
all the
intersection.
ranges, we'll take the intersection.
Intersection. Okay,
Yes,
so it's greater than equals. Okay, yes, fine. It's so
we'll
it's
take the
minus
intersection.
17 plus minus.
Yeah, here we take only the positive value, this one, real value.
Okay, our k should
Okay.
be greater than zero. So only the last intersection we are getting,
Yes,
that is k greater than zero. Okay, we will take that
yes,
answer.
yes, yes. So we'll take the intersection. That means if you see that, so first one says k is greater than 0, correct? So
Hmm.
this one
The
says
second
that
one is k is greater than
minus
minus 20.
25. Okay, third one
Yeah,
says that minus 17.
minus 17, and it's also having poles on
Okay,
this.
so this is the intersection. So that is k is greater than 0. So when you take k is greater than 0, any value if you substitute into this equation, so
The
all
system will be
roots,
stable.
no, simply if you substitute k is greater than 0, any value, okay,
Hmm.
so you will get all roots with negative real parts. Is that clear?
Yeah.
You will get all roots with negative real parts. Negative real parts means what?
Yeah. Yes, fine, fine. Negative real
Ne-
poles means our system is stable.
So yeah, negative real poles means the poles can be anywhere here.
So here we took like our 25k or greater than zero. We are taking all the thing are to be zero, greater than zero,
Yes, yes,
as to make the first column my positive. Can I
yes,
substitute?
exactly.
Can I also take like all the first column elements should be negative?
Yeah,
Acha,
you can
25
also
is there. So
no, no, 25 is already a positive value. That's why we took the
we
other
cannot take
values
that.
are positive. Is this clear? So now what the RH criteria can be used to find the range of the K for which the system is stable. Okay. So basically what is K here from the block diagram?
So
What is
k is
K?
my one function in between
So this is controller gain.
controller gain.
Okay. So what
So
is
our
this
controller
controller
gain should
here?
be positive.
So this is proportional controller.
Okay.
Okay. What if this controller is PI controller?
So it would be ki by s.
We will be having QP plus KI by S,
Kp plus ki by s. Okay.
right? So if it is PI controller, okay, so my expression, this expression will be in terms of what? KP and KI,
Ks. Ki.
okay, and again my first column is going to be again in KP and KI.
Okay, here the controller
So
is k as per the question. So my variable is only k. But if I
yes,
taking the pi controller or like pd controller, then two
yeah,
or three variables can also be there according to the
yeah.
controller's ability.
If you go for PID, then your equation is going to be KP, KI, KD. You have to find the
And
common range, the region which covers these three. Clear?
the one more thing, like here we have got 25. If the coefficient of s cube it's negative, then I will take the condition
Yeah,
like
you
less
can
than
take the
zero, less than
negatives and
0.
verify that. Okay.
Okay. Then my k,
Yeah.
just take an example. Then my k would come on the left side. Not like here it came the right side of the zero. Then it would come on the left side.
Yes. Yeah. K will
Or
be
as per
negative.
the or as per the
That
reason.
depends.
It
Yeah,
depends.
that depends because this expression is big expression will plays major role.
Yeah, yeah, yeah. We
Okay.
cannot tell. We have to solve it.
Yeah. Yeah. So that is first problem. Okay. So this is for another case when p is equal to 0. Okay. So here also you'll be getting the same kind of thing. So I'll after this live session, after passing this PDF, you please check that. Okay. Then, so
Yes.
coming back to the special cases. So now let us consider this example. Okay. S power 5, S power 4, 2s cube plus 2s square plus 3s plus 5. So you can see here, first what we are doing is, so we are writing all the terms in the vertical way here. S power 5, S power 4, S cube, S square, S power 1, S power 0. Okay. Then we will write the coefficients in the first two rows. Okay. S power 5 coefficient is 1. S power 4 coefficient is 1. S cube is 2. S square is 2. S is 3. And S power 0 is 5. Okay. Is this clear? Any doubt? Okay. Now you will be doing the calculations. Okay. So what are the calculations? So first 1 multiplied by 2, this 1 multiplied by 2, divide by 1. That is giving me 0. Is this clear? Okay. I think this is the same problem.
Yes. Yeah.
Yeah.
Yes.
Yeah. Same problem we saw. Okay.
I guess it's same only, no? No,
Yeah.
it's
Yeah.
little different.
It's no. It's the same the expression.
Okay.
Okay. So
It's
here anyway, let us continue this. So you are getting
hmm.
0. Okay. The second one is,
Okay. We will take epsilon instead of
yeah,
zero.
no. Then 1 multiplied by 3,
Okay.
1
Huh.
multiplied by 5, divide by this one only. You will get this one,
Minus two.
minus 2.
Hmm.
Since there are no terms here, we'll take this is a
We will
0.
take zero on the third column
Yeah.
afterwards.
Now you see, if you are trying to finding this, because of 0, you'll get infinity here. Okay. Because something by 0 is infinity. So you cannot continue the calculation. So you replace 0 with epsilon and continue the calculations. Then it will become epsilon multiplied to 1 multiplied minus 2. So you will get this expression by epsilon. Similarly, continue the calculations. This one and this one divided by this. You will get this expression, which is nothing but this one. Okay. Now take this limit epsilon tending to 0, all these three terms. This one, and this one. Okay. So you will be getting as two sign changes. So that means two poles on the RHS S plane. Okay, hence the system is unstable. Is this clear? Any doubt?
Just wait. I will check.
This will be positive. This term is positive. This term you will get
Uh,
negative.
Negative. Then again the
Yeah.
other. I am getting positive. So two times sign changes
Yes.
there.
Yes. Okay. That is special case one. Next, special case two. So again, expression is given to you. So this expression. Okay. So you put the terms in the first. You will be writing these terms s power 6, s power 5, s power 4 cube, s square, s power 1, s power 0. Then put all the terms in two rows. Is there any doubt here? Any doubt?
We
No, I guess.
so
Okay.
we'll take
So
our
this is,
auxiliary.
yeah. So this
We will
is
take our auxiliary
s,
equation here.
yeah, s power 6 coefficient, s power 5 coefficient, s power 4 coefficient, s cube coefficient, s square coefficient, s coefficient, s power 0 coefficient. This is just we are taking 0. So it means that all even numbers here, all odd numbers here, coefficients. Okay, then we continue the calculations. So you can see here, first this row, s power 4 row. Okay, what we do? This multiplied 5, 15 minus 9, 6. 6 by 3, that is 2. Clear? Let me remove this. Okay, that is 2. Next, 3 multiplied 8 minus 1 multiplied 6. 24 minus 6. Okay, that is 18 by 3. That is 6. Next, 3 multiplied 4, 1 multiplied 0. Okay, by 3. That is 4. The last term, since there are no terms, this is 0. Is this clear? Any doubt in this?
Sir, that 6 would be 4, no? That 8 3 is
This one,
16. Oh, so sorry, 3 is
24. 24
fine,
minus
fine.
6.
Ah, yeah, 24 minutes.
Yeah. Okay, clear? Next. Okay, so fine. Next. So 2 multiplied 9, 18 minus 18, 0. Then 2 multiplied 6, 3 multiplied 4, 0. These two are zeros, you get 0. This is extra 0 we are taking. Now you see row with all zeros. Row with all zeros. So what we do? Special case 2. Row with all zeros. Is this clear? Any query?
The
So row,
auxiliary question,
yeah,
what
yeah.
we got.
Because we have taken a row with, we got row with all zeros. So we went for this. Sorry, we are going for this auxiliary equation. What we do auxiliary equation?
Huh,
So we will
just
see. We
how
will
we
take
took s to the power 4 means 2 s to the power 4 plus 6 s to the power 6
s square.
multiply with
S square.
s square.
Yes.
Hmm. Fine, huh? Okay.
Yeah. Then 4. Then we take the derivative. We get 8s
So it
cube
will
plus 12s.
we will take the power of the s by doing minus 2 means or all the even side after 4.
Yes. Yes.
I mean before
All
4.
all even numbers.
Okay. Like if it would be 3, then I will be taking s then 0.
Yes. S cube yes and 0. S cube
Hmm.
yes only. You don't
Hmm.
get 0.
Yeah.
0 goes to even line. Okay.
Huh.
So then you get 8 here, 12 here. Okay. Replace this 0 with 8, this 0 with 12. Okay. Then continue the calculations with these numbers, new numbers. Okay. So then check for these sign changes. Then check for the sign changes. So you will see no sign changes. Okay. And you got this auxiliary equation. Okay. System is marginally stable because this auxiliary equation will give us the uh, complex conjugate rules. Okay. Here you see no sign changes in this column. Okay. Any queries? Okay. Fine. So system is marginally stable because we are getting the auxiliary equation is giving us the uh, uh, roots on the imaginary axis, plus or minus a1 plus or minus a
Sir,
root
just can
2.
you show the last line? I was just
Yeah,
checking that.
yeah.
We will got 3. Then 4. Yeah. So we are not yet. There is no sign change in the first column, so it's stable.
Yes, exactly. No, no, it's not stable. It is not unstable.
Acha, it's marginally stable.
Yeah. Because the auxiliary equation is giving the roots on the imaginary axis, these roots.
Okay, yeah, we have to also find
Yes.
the roots of the auxiliary equation.
Yes. Okay.
Hmm.
So that is marginally stable. Okay. Yeah.
Yes.
Next. Next is open loop transfer function is given to
Sir,
us
sir, one
with
doubt.
yes, yes.
So the auxiliary equation, the roots that we get for that,
Okay.
so that also they are the roots for the actual characteristic equation also, is it?
Yeah, yeah, yeah.
Okay.
Yeah. Okay. So here open loop transfer function g of s is given to us. Unity feedback, that means h of s is 1. G of s is given to us. We need to find the values of a and b. Okay. So where they are they are in the g of s expression, and system has to be marginally stable, and find the marginally stable, and it is getting oscillated. Find the frequency of, it has frequency of 4 radians per second. Okay, this is the reverse question of that previous question. When the system becomes unstable, when you have roots on the z omega axis, when you have roots on the z omega axis, when you get the auxiliary equation, when you will get the auxiliary equation, when a particular row is all zeros, correct? So you have to go it in the reverse way. Is this clear idea? Okay, so first what we do is we are finding the closed loop transfer function. So this is the closed loop transfer function. Okay, so g by 1 plus gh, substitute expressions for g of s and h of s. Okay, so this is the expression. Okay, so then characteristic polynomial is denominator, make it equal to 0. Okay, now write down the RH array. RH array. So how do we write? S cube, S square, S power 1, S power 0. Then what are the terms? Okay, so the terms are, first S cube coefficient is 1. Next S square coefficient is A. Next S coefficient is 2B. Next S power 0 coefficient is 4. Is this clear? So first term, this term, how do we find? A multiplied 2B minus 1 multiplied 4 divided by A. So that is this term. Next, what we have here, since we don't have any terms there, this will be 0. Then this multiplied 4, A multiplied 0 divided by this total term, that will be 4. Is this clear? Okay, so now the
Yes, yes.
now yeah, now the question says that, again look back to the question, we need to find AB such that system is marginally stable. Okay, previous question we saw, when the system becomes marginally stable, when you have roots on the z omega axis. When do we have roots on the z omega axis? When you get this auxiliary equation situation, correct? So you should get this auxiliary equation situation. So when you get that auxiliary equation situation, when a row will have all zeros. Okay, now you see here, which row is having zero option? This row. Already one element is 0. Okay, you can make this term equal to 0. Then this row will become zeros. Correct? For marginally stable. Is this clear? Okay, so from this you are getting a
Yes.
condition of AB equal to 2. Okay, AB equal to 2.
Okay.
Now you are considering the auxiliary equation, that is auxiliary equation. How can you consider? This is the row with all zeros. Okay, auxiliary equation, what you do, you take the row above that, that becomes as
The
squared
auxiliary equation is
plus
our
4
a square plus
plus 4.
4.
Okay,
Hmm.
as
Yes, plus 4.
squared plus 4 s power 0. Okay, now we said that the system is oscillating with a frequency of 4 radians per second. That means omega is 4 radians per second, that is given to us.
Omega is.
Okay, so
Yes.
then substitute s equal to j4.
Okay,
S is
so
nothing
in the
but j
question it's
omega.
given that it's oscillating. Therefore, we are
It
taking
is
it
already
is a
oscillating.
marginally stable.
Yes, yes, exactly.
Oscillating means it's a marginally stable.
Yes, yes. So S is equal to plus or minus J4. Okay, substitute in that. So you already know that J is equal to root minus 1. Okay, substitute that also. So you are getting A as 1 by 4. And you have this expression already here. Okay, so you'll get B as 8, A as 1 by 4. For these values, system will become marginally stable for the given frequency. So it will oscillate at that frequency. For A is 1 by 4, B is 8.
So for
Okay.
these values, the the condition given in the question got satisfies. That is oscillating.
Yes, yes, exactly, exactly. It will oscillate with 4 radians per second. If we want to it to oscillate at 10 radians per second, the values of A and B will change. Because here we will substitute to 10 in place of 4. So then this will become 100. So you'll get different value. Okay. Yeah. Any queries? Okay, so now next question. So we have this uh, feedback control system. Okay, so where we have a plant transfer function is 5 by s into s plus 10, and this is the controller. Okay, what this controller is doing, it is taking the output and passing through this controller 2 plus ki by s. Ki is the gain here, and giving it to this plant summing point. Then the error signal is applied to the plant. Okay, now our question here is to find the range of the ki, okay, which gives us the total closed loop system stable. Okay, so again same thing. So find the transfer function. So that is nothing but, let's say this is g, this is h. So same way g by 1 plus gh. Okay, so this expression numerator by denominator. Okay, then characteristic polynomial d of s equal to 0, denominator equal to 0. So again follow the same procedure. Okay, so what do we do? S square s cube 10s square 10s plus 5k I. So s cube s square s and s power 0. Okay, so fill the coefficients in the first two rows. S cube is 1, s square is 10, and s is 10, and s power 0 is 5ki. Okay, so this we know how to calculate, that is 10 multiplied by 10 minus 1 multiplied 5k divided by 10k, and this is 0. So this already we know, this multiplied this minus 10 multiplied 0 is 0 divided by this expression, that will give us 5k. Now we are saying that system must be stable for which values of ki? That is our question. So what do we do? So here already 1 and 10 are greater than 0. So we have to make other two terms also greater than 0. Okay, other two terms means this is first term, this is second term. First term gives ki should be greater than 0. Second term is this. Okay, 100 is greater than 5 ki. 20 is greater than ki. Ki is less than 20. So what it says, so this is 0. Okay, so this one. Okay, ki is less than 20. So this is 20. It has to be less than 20. Okay, so now what is the intersection? Intersection is this.
0 to 20.
Yes.
The k belongs
So
to between, or the ki, here ki belongs
yeah,
to 0 to 20.
0 is less than ki is less than 20. You take any value of ki and substitute here, or
Yes, yes, yes.
substitute into this expression, will make your system stable. System stable in the sense, you take any value of ki. Okay, for example, you take
Between 0 to
ki is equal to take some 5.
50.
So you will get roots with negative real parts. You will get roots as with negative real parts. So what do you mean by negative real part? First term is negative. The second term you can have anything, positive or negative, does not matter. The imaginary term. Okay, is this clear? So that is how we'll get
Means it will come
any
on the left side of our
yeah.
j omega.
Yes, exactly.
Yes.
If there is no z term, you'll get the root on the real axis. If there is a z term, so it will be non x-axis, but it will be on the right side of the z omega axis. Sorry, left side of the z omega axis. Okay. Any queries in this problem? Okay. Next. So we have this teleoperated control system. So where we have the operator can be
No,
a
sir, it's fine.
remote operator, or the operator can be a human operator. Okay. So here the problem says that we are getting a control system characteristic equation of this one. Okay, which has two constants. Controller has two constants, that is K1 and K2. These are the two feedback gains, as I was saying recently. So the controller could be a PD controller or PI controller. Okay, so this is the characteristic equation. Now let's start with that. So you're writing s power 4, s cube, s square, s power 1, s power 0, and fill these first two rows where s power 4 is 1 coefficient, s cube is 20, s square is k1, the s is 4, and s power 0 is k2, and last one is 0. Okay, so forward with the calculations, proceed with the calculations. Okay, so this one, how do you get? 20k1 minus 4 divided by 20. Okay, this one 20k2 minus 0 divided by 20, so that is k2. The same way this will become 0. You can get also this one, so that is nothing but, so this multiplied 4 minus 20 multiplied k2 divided by this. So this is the expression you are getting. Okay, so this expression. So final one is k2. Now You wanted to make your system stable. So unlike the previous problems where we have only one variable, so you can able to show that variable on the single axis, a real line. Okay. Whereas now you have two variables, that is k1 comma k2. Okay. What do you do is, so follow the same way. First, last expression, k2 is greater than 0. Then this expression 20 k1 minus 4 by 20 is greater than 0. This one, which gives k1 is greater than 1 by 5. Whereas the third one, this one, okay, which gives this expression, okay, which gives this one. Okay, here it is like a straight line, but inequality is there, greater than 1. Okay, so suppose if you take 5k1 minus 25k2 equal to 1, okay, you will get k2 as like this, k2 as in this way. Okay, so what we are doing here is, so you are taking, we are taking x-axis is k1, so y-axis is k2. Okay, x-axis is k1, y-axis is k2. So we have three conditions, 1, 2 and 3. Okay, so
Okay.
what you need to do is you have to find the common region between k1 and k2 which satisfies these three conditions. That is our problem, correct? So what is the first region? K2 greater than 0. K2 greater than 0 is above this direction, correct? Above this direction, okay, above the
Yep.
k1 axis. Okay, then k1 is greater than 1 by 5 is what? You have this line, 1 by 5 means 0.2. Okay, right side of this line, clear? Yes or no?
Okay. So
Okay, now
here
what
we
is
are
the common region between these two? Now can you tell me? The common region is
that
this
green
one,
part.
this one. No,
That
no, it
green part.
means between this one and this one, the common region is this, correct? Now you see this equation, 5k1 minus 25k2 equal to 1. What is this? It is a straight line equation, where that straight line equation represents, if you take k1 is equal to 0, what you get?
K1
If you take,
equals
sorry,
to
sorry,
0.
not k1 0. If you take k1 is equal to 0.2, what you get? K2. So this expression, correct? Okay. What is that value? That will be 0. This one. Yes or no? 0.2 means 1 by 5. 1 minus 1, 0 by 25. This one. Okay. So if you do the, if you draw this line, 5k1 minus 25k2 equal to 1. If you draw this line, the line goes like this. Okay. And 5k1 minus 25k2 is greater than 1 means this direction. This direction. Okay. So it means that finally this green part is the ratio. Is this clear? is this clear?
Little
Any
no means okay, k1 k2 we understand, but how to take the intersection, because earlier questions we
no,
took
no,
only one variable
no.
as k.
Listen. So the what is the third condition? 5k1 minus 25k2 greater than 1. Okay. So first draw this line.
Which one?
5k1 minus 25k2 is equal to 1. Okay. Draw that line. Okay. You know how to draw this line. Take some value for k1, find k2. Take another value for k1,
Yeah,
find k2.
k2 is
So
our y-axis and k1 is our x-axis. That is
yeah,
fine.
so this is that line.
Okay, yes, this is also got understood.
Okay,
That's the
so if you
function.
take point,
We just
if you
taken
take
as
point
a function.
two, if you take point two, you'll get 0. If you take 1, you'll get this one. If you take 2, you'll get this. So connecting all the points, this is the line. Okay.
Yes,
Now greater than 1.
greater than one. Okay,
Okay. So substitute any value. Let's say here this value. Substitute this value. What is that value? 1 and something like 0.16. Okay. Substitute any value. Let's say 0.1 and 1. 1 comma 0.1. Okay. Check that value is this side or this side.
lower side,
I mean whether that is greater than 1 or less than 1, because
less than.
this is what this is equal to 1, no? So greater than 1 or less than 1, it will be greater than 1. It means that this side. So what is that region is? This is the region greater than 1 means.
Okay,
Okay, now what is the intersection? Intersection is this green region. Okay, so you please draw it, these three conditions. Okay, you will understand it. What is the common region? So it means that if you choose any value between k1, value of k1 and k2 in this region, okay, it will make this characteristic equation all roots as stable roots. Okay,
okay.
yeah, that is the expectation here. We need to find the k1 and k2 range, this green region.
So we will draw a graph
Yeah.
on
So
basis of
please
k1 k2.
please draw and check it. Okay, so that is another kind of problem. So this is also similar way. We have open loop transfer function, unity feedback. So now here two unknowns we have, k and t. Okay, again we need to find this region. Okay, so where the closed loop system becomes stable. Okay, so again what we are doing is we are finding the closed loop transfer function, characteristic polynomial. So this is the expression. Okay, so again do the same thing. So now you are getting three conditions. So another condition is this. Okay, so follow the same way. Here what we are doing is, so we are considering two ranges. K is less than 0, less than 1, we are taking some values, and k greater than 1, we are taking some values, and checking t behavior, whether that is positive or negative. Okay, what we need here is this expression must be greater than -2. Okay, so it means this is our requirement. No, sorry, this is our requirement. t is giving us positive values greater than -2. So again, if you plot k on x-axis, t on y-axis, you will get this is the ratio. Okay, so that you please verify it. If you don't understand, please ask me next again or in the chat box. But you have to verify these four conditions. Clear? So it is just like the previous problem.
Okay, so here we
Okay.
have two variables t and k.
Yes, yes. Okay, again, same way. So you wanted to check this line. So draw this line first. Draw this line equal to -2. Okay, and choose the region which is greater than -2. Then it will be easy for you. Okay, so that is another kind of problem. So this problem is straightforward for a given circuit. Okay, RC phase shift oscillator. Okay, so you have to find the transfer function first. Transfer function is V2 by V1. Okay,
As
where
given the
V2
question.
is the output equation. Okay, V1 is the input voltage, output voltage and input voltage. Okay, so first what you do is you will write the KVL equations. I'm leaving that one to you. I gave the equations. Okay, here our job is to find transfer function or voltage gain V2 of S by
Yes,
V1 of
v1
S.
of s.
Yes. So what we are doing is, since we have three equations and three unknowns, here in this, okay. So from matrix theory, we are using this Cramer rule. Okay, to find this I3. What are the unknowns? So I1, I2, I3. Okay, I1, I2, I3 are the unknowns. Okay, so first what we do, from these three equations, using this Cramer rule, we are finding the I3 expression. How we are finding I3 expression? So we are taking this determinant and this determinant. So what is this second determinant? Basically, you can see first term, the second term, third term is 0. First term, third term is 0. Similarly, from the second equation, minus r, so this term and minus r. Similarly, for third equation, first 0, second minus r, third one is this. This is dead. So the Cramer's rule, what we do to find I3, which is the third variable, simply we replace these elements with these elements in the numerator. The remaining two columns are same. Okay, so you can check that. Just you can find the Cramer's rule example also. So then you are finding the I3. So once you have I3, my V2 is RI3 from the circuit. So V2 is in terms of V1. Okay. So we are finding the expression V2 by V1. That is our question. Okay. So that is the transfer function. That's the transfer function. Okay. Any doubts? Now, so We know the gain of the inverting amplifier V2 by V1 is minus K, that is minus R1 R2 by R1. So this expression. Okay, so once you substitute, so your characteristic equation is becoming like this. Okay, so this is like numerator by denominator. Okay, so the denominator is this, d of s equal to 0. Okay, so you can see these are all simplifications only. So now we are, what we are doing, this is the expression. Okay, so again finding the RH array. Okay, so first term is this, second term is this, then the third term goes here, so this s should not be there. Okay, then final one here. So you will find this term again following the calculations in this way, then you'll get this one here. Now for the system, because we are talking about the oscillator, okay, we are talking about oscillator. What does it mean? Oscillator means it has to oscillate with some frequency, correct?
That means it's marginally stable.
Yeah, so sorry.
That means it's marginally stable.
Yes, exactly. So marginally stable. So to make marginally stable, okay, we should get a row of all zeros, correct?
Yes.
So that is this one. For if you take k is equal to 29, if you take k is equal to 29, this term goes to 0. Then you'll
Yes.
have both the zeros. Okay, that's what we are checking the condition. So for k is equal to 29, so this row goes to 0. Okay, now you'll have this auxiliary equation. Auxiliary equation is what? This one, the row above the all zeros row. So that will be, auxiliary equation is 6 r square c square s square plus 1 multiplied s power 0, correct? So this expression. Okay, so if you solve this equation, that means if you solve for s, so what you get, s is equal to z omega. And omega, what do you have? 1 by root 6 rc, that is the frequency of oscillations. Is
For
this
k
clear?
equals to 20.
K equal to 29, this term is becoming 0. In that way only we will get all row, all that entire row becomes zeros.
So for that, the condition was given it's oscillating. So we are taking it
Yes,
0 and k equals to 29, then we are proceeding
yes, exactly. So
with the auxiliary
that is our
equation.
question. That is our question.
Okay.
Okay.
So this is only the part A.
No, part B. This part B is also over.
Ah, okay.
When you take, you have to, if K is equal to 29, you will choose your resistors in that way. These resistors. That is kind of design problem. Okay, you wanted to make oscillator to oscillate at this frequency. So you will choose your resistor so that your oscillator will oscillate with this frequency. Okay, so that is one more problem. Next, so open loop transfer function is given to you for unity feedback. Okay, now this open loop transfer function has two constants. So one is A, another is B. Okay, you wanted to make your closed loop system stable. You have to find the range of k for various cases. Okay, so first, as usual, what we do, we find the closed loop system transfer function. Okay, then characteristic polynomial. Okay, you wanted to make the closed loop system stable. Okay, so s square s bar 0. Okay, so here already 1 is positive. To make the system stable, what we do, take k minus b greater than 0 and this also greater than 0. These are the two things, correct? So first case, what is the range of k we need to choose in such a way that system has to go to stable. So first case is if a is less than 0, b is less than 0, what will happen? If we take a is less than 0, so a becomes negative. This whole term goes to the k must be positive for making this greater than 0. If b is less than 0, you have to take k is greater than 0. Is this clear? Any doubt?
No, it's clear.
Yeah. So till this point it is clear. Yeah. So now what is our condition here? K must for the system to be stable, k must be greater than b, and minus ka must be greater than 0. Clear? Okay.
Yes.
So now let's say if you take a is less than 0, b is less than 0. To satisfy these two conditions, what should be the value of k? If you take a is less than 0, okay, when this term goes to greater than 0, only for positive k.
Yes.
If a is negative, if k is
Then yeah,
positive only, the total term
only
goes
for
to
positive.
greater than 0. Okay, that is first thing. When b is negative, okay, if I take k negative, that's not possible. So I must take k positive. If I take b is equal to minus 3, okay, if k is any value which is greater than 0, this condition is satisfied, correct?
Yes. Yeah.
So
If
what
we
is the
take
common
k is greater
condition?
than -3, then it could be -2. So that's not possible.
Yeah. So we have to find the k for which satisfies both these two for given values of a and b. If a and b are less than 0, k must be greater than 0 to satisfy these two conditions, which makes the system stable. Okay. Next case, a is less than 0, b is greater than 0. So in this case, when a is less than 0 here, k must be positive. That's clear.
And in the
Okay.
above equation, k is
If
greater than
b
b.
is greater than 0, if b is greater than
So
0,
the intersection is k is greater than b.
yes, k must be greater than b. Then only these two expressions gets satisfied. Okay. Similarly, the other things also. So let's choose this one D. Okay. A is greater than 0, B is greater than 0. If A is greater than 0, what will happen?
Then k would be less than 0.
K is
And
less
then
than
k
0.
will
To
be greater
satisfy
than b.
this,
So k will
yes,
comes between 0 and b.
K is greater than B
And here
because we
k
have
is
to
greater
satisfy
than.
that condition.
Okay.
K must be greater than B. So it is like B is already positive. So in
Okay.
one case, K is greater than B. The other case, K is less than B. So we cannot find any value of K which makes the system stable.
So both A and B could not be together be positive.
Yes, yes, yes. So other three cases it is fine.
Other three cases the system would be stable, but in the case D,
No, no, no,
it
not like that. We can find a k which can make the system stable. The fourth
okay.
case is we cannot find any value of k which makes the system stable.
Acha, there is no existence of the condition for the value of
No,
k.
the last one.
Hmm. Yeah, the last one. The
Yes,
last one only I
yes,
must.
yes. Okay.
For the condition A and B is positive, there is no
There is no existence of
value of k.
k.
Hmm.
Yes.
Value of k.
Okay.
Yes.
Yeah. So this problem also, okay, let's see this one. I think it is last one. Okay. So here, this is the block diagram given to us. So here there is no doubt we will be finding y of s by u of s expression. Okay. Where this h equal to 1 here. So we will be finding that as k, like g of s k by 1 plus g of s k. Okay. So what this one says is, okay, so where k is the proportional controller here. So we need to determine the range for k, range for k, so that this is important. The impulse response of the system decays faster than e power minus 2. Impulse response of the system decays faster than e power minus 2. That means what? So e power minus 2, so it starts at 1, it goes to like this. This is e power minus 2t. Okay. So e power minus 2, basically 2t means basically what? So in the system, there is a pole at minus 2. There is a pole at minus 2. So, okay, it reaches very fastly means what? It should be something like it has to go very fastly. It will be even more e power minus, which is a value maybe 70. Okay. So that means what? That minus 7 is somewhere here. Okay. That means what you are trying to do here? You are trying to finding this region. What is that region? It is this region is nothing but what? LH
So are we
side
taking a
of,
Laplace transform?
and that is the question.
Like e to the power minus 2 is if we take in Laplace domain, then it would be 1 upon s plus 2.
Correct.
So that 1 upon s plus 2, that means minus 2. Okay.
E power
Okay, yeah.
minus 2. So we are
We have
saying
drawn
that it
that
has to go very fast means e power minus 70, minus
on the
80,
left
etc.
side of
Yes.
that reason.
S equal to minus 2.
Yeah.
Is that
For s
clear?
equals to minus 2, it should
Huh.
come, s should be less than minus 2.
Yes. So what is this one is, this is S is equal to minus 2.
Minus 2.
This is what S is equal to
0.
0. Right? Now what is our question is, you need to
Should decay
find the
faster
range
than
of k. No, no, you need to find the range of k
range of. For that, s
for
should
which
less than minus 2.
system is stable, means the new stability definition is to have all the poles left side of minus 2. Is this clear? So this is our
Yes.
question. To find range of k, where that range of k, if we substitute any value from that range in the system, that will give us the poles location here. Is this clear? Which is
Okay.
left side of this s is equal to minus 2 line. Okay. Okay. in all previous problems, what we tried was left side of s is equal to 0. Okay, now we are trying to looking for left side of s is equal to minus 2.
Minus
Is
2.
this clear? Okay, now the new j omega axis is what?
Minus 2.
This is j omega. New j omega axis is this one. S is equal to minus 2. Is this clear?
Or we can say j omega plus 2.
Yes. So that is what we are going to do here. So we will be finding this expression first. The closed loop transfer function gk by 1 plus gk.
What gk?
Okay. N of s by d of s. Then characteristic equation is this one. Okay.
Yes.
So this expression. Okay. So what we are looking is the impulse response. Sorry. The impulse response will decay faster than e power minus 2t if all its real part roots of f of p of s are strictly less than minus 2. Clear? Okay, so now what we do is we will take the help of the RH criteria and check or find the range of k for which the system is stable for the new axis. Okay, what we do here is we do the transformation from S to S cap. Is this clear? So where this is nothing but S is equal to 0, this is nothing but S is equal to minus 2. Okay. So simply what we are going to do is we substitute S is equal to S cap minus 2. Okay.
Okay.
So in the P of S, we substitute P of
Okay. We
S cap
substitute
minus
s
2.
cap minus 2.
Yes. Then this expression. Okay.
Makes sense.
So yeah. So the
Okay.
entire equation is in terms
Then
of
we will be table according to the s cap, not
yes,
s.
yes, yes. Okay. We are solving the problem and finding the range of k.
Okay. 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 Yeah.
So when the k is between 26 to 30, we will get all poles left side of s is equal to minus 2.
So it between 26 to 30. Okay.
Yes.
Then we will get holes on the left side of.
S is equal to minus 2.
Yes.
Or you can say S cap equal to 0. Okay.
Our new x, our new
Yes,
geometry
yes,
axis
yes, yes. So we are simply shifting the origin to S is equal to 0 to S is equal to
on the left side.
minus 2. Minus 2. Then we are checking
Or we can say
that.
that for s plus 2,
Uh,
the k value should be come between 26 to 30 for the condition given in the question that it should decay faster than e to the power
yes,
minus 2.
yes, 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 exactly. Because those poles are left side of S is equal to minus 2.
S equals to minus 2.
Yeah, that's why I took here example as S is minus 7. That will be left side of S is equal to minus 2.
Minus 7 is left side of minus 2.
Yes, yes. Okay,
And for
so
s cap, if you say that it would become minus 5.
sorry, S cap.
If we take like for s is minus 7 and for s cap if we take then it become minus 5. uh,
No, no, no.
just like minus 2 if you take 0 in the terms of s cap,
Minus,
not in terms of s.
minus. No, if we take no, we should not take the difference. Now the new
Okay.
origin is s is equal to minus 2, new z omega axis.
Yes, fine. Fine,
We're
fine. Got
simply
it.
shifting that. Yeah. So we'll stop here and continue in the next session. Okay.
Sir,
Yeah.
please
Yeah.
share the link of this.
Yeah. We'll share now.
That
Okay.
you don't
I'll
have to
share
upload
the.
it to, yeah, directly direct link. That
Oh, okay.
G.
The issue is that we are staying in a place where internet is very slow. So that's why we
Okay.
gave those temporary link. Okay.
Yes, sir.
So whenever we get the sufficient internet, we'll upload that also in live sessions. Okay. As
Fine, sir.
of now, you please watch those, and this PDF also I'll share with.
Yeah, PDF and
Yeah.
the temporary link also you give, sir.
Yeah. 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 For this one also I'll share now in half an hour.
Yes, sir.
Okay.
Okay.
Yeah.
Okay.
Yeah. Thanks a lot.
Thank
Yeah.
Thank you, sir.
Thank you.